when you break your arm, an X-ray gives you a clean binary answer. Like you look at the film, you see the jagged white line through the bone, and the diagnosis is absolute.
Yeah, broken or not broken, it's incredibly straightforward.
Right, exactly.
Yeah.
And it is immensely comforting to have that level of mechanical certainty. But when you hand over the keys of your enterprise to a large language model, that X-ray machine just shatters into a million pieces.
Oh, completely. You go from absolute certainty to a black box of probabilities.
Exactly. You are suddenly trusting a system that operates on hallucination-prone probabilities to make, well, highly consequential deterministic decisions for your business. Imagine you're a CTO right now.
Trying to keep up with the hype cycle.
Right. Your board is demanding that you implement autonomous AI agents to cut costs and accelerate operations. But your CISO is threatening to resign because the moment you send proprietary data to a cloud API, you've created a massive problem.
A completely unpluggable security breach. Because you're giving an unpredictable language model the power to execute code on your servers.
Which is terrifying. So today, we are tearing apart a system that finally fixes that broken X-ray. It's a high-energy, fast-paced, deep dive into a really impressive hackathon project.
Yeah, we are looking at a fundamentally new paradigm for enterprise architecture here.
So let's set the stage. What are we looking at today, and where did this come from?
The project is called the Sovereign Agent Fleet. It was submitted to the AllThingsAgenticHackathon specifically for the Fortified Enterprise Fleet track.
And we are pulling straight from the developer's GitHub repository for this, right?
Yes, the handle is cleardaniel/Sovereign Agent Fleet. We're looking at their code, their architecture docs, and this really dense, fascinating companion white paper called Sovereign Knowledge Systems.
Okay, so what is our mission today with this deep dive? Why should you, the listener, care about this specific hackathon project?
Because it proves a massive point. It proves that you do not have to trust the AI model at all, like zero trust. You can build a system where the AI is treated with complete suspicion, yet you still harness its massive cognitive power.
I love that. Let's anchor this in the reality most developers are living right now.
Yeah.
Because the central tension in the industry is this mad dash to build multi-agent systems, right?
Oh, everybody wants fleets of bots.
Yeah.
Analyzing data, writing code, responding to cyber threats.
Trading stocks, you name it. But the standard way people build these things, usually by just gluing together some LangChain scripts and calling it OpenAI or Anthropic API, it means you are surrendering your data sovereignty entirely.
You're just piping your crown jewels out to a server you don't control.
Exactly.
Yeah.
And even if you pull the model down and run it locally, on your own hardware, you are still letting a probabilistic guesser drive the car.
Right. Because the standard multi-agent framework today is really just a thin wrapper around the language model.
It's the brains and the brawn.
Exactly. The model is the brain, the orchestrator, and the executive all rolled into one. It decides it wants to run a tool, and the framework essentially just acts as a courier, right? Handing the tool over.
So the model itself is the governance.
Yes, which is exactly the core problem.
That's terrifying because models hallucinate. They get confused by prompt injections. Like if I bury a malicious instruction in a PDF that the agent is supposed to summarize.
The classic invisible text attack.
Yeah. And that instruction says, delete the database. Standard frameworks might just say, well, the model requested the delete tool, so here you go wild.
That is the exact vulnerability that Sovereign Agent Fleet eliminates. Completely. It approaches the problem by separating what the system believes from what the system is permitted to do.
Okay, wait, unpack that for me, because that sounds like a very subtle distinction, but I feel like it's the whole ballgame.
It is the whole ballgame. In the white paper, they formalize this as invariant one. They call it the authority non-equivalence principle.
The authority non-equivalence principle. Okay, give me the mechanical breakdown to that.
In absolute mathematical terms, it means model output does not equal authorization.
Wow. Okay.
To understand how radical this is, think about the AI model as an incredibly brilliant but wildly reckless intern.
I love this analogy. A brilliant intern.
Right. So this intern went to MIT. They can read 1 million pages a second, and they generate phenomenal ideas. But they are also prone to making things up, getting easily tricked, and taking massive, uncalculated risks.
Honestly, that is the perfect description of a large language model.
Right. Now, in a normal agent framework, you take this brilliant, reckless intern, you hand them the master keys to the server room and the corporate bank accounts, and you say, go optimize our infrastructure.
Which is literally a recipe for a resume-generating event.
Whoa.
You are going to get fired.
Precisely. You'd never do that in real life.
Yeah.
So what Sovereign Agent Fleet does is introduce a strict, unyielding, mathematically rigid manager.
Okay, so the manager is a separate component.
Entirely separate. The intern is allowed to do all the research they want. They can read the documents, analyze the network traffic, draft up the most persuasive, highly confident proposal in the world.
But they can't actually do anything with it.
Exactly. They cannot physically touch a single system. They have to slide their proposal across the desk to this manager, and the manager holds the actual keys.
So the manager decides.
Deterministically. The manager decides what gets executed based purely on corporate policy, cryptographic identity, and verifiable capabilities. The manager literally cannot even see the intern's confidence score.
Wait, hold up. Let me challenge that. I'm going to put on my skeptical judge hat here.
Go for it.
If this manager is completely frozen and deterministic, doesn't that make the system incredibly brittle? I mean, the whole appeal of AI is that it's dynamic, right?
Sure, you want the adaptability.
Right. So if corporate policy changes during a crisis, let's say we are under a cyber attack and we need to instantly isolate a subnet we don't normally touch. If the manager is just this dumb frozen script, aren't we just trading AI hallucinations for bureaucratic gridlock?
That's a very fair concern.
Like we're going to get hacked while the manager's just sitting there saying, computer says no.
A critical question. And it forces us to look at how the architecture actually manages state and policy updates. So the manager, which in the code is literally a single frozen function called decide.
Wait, just one function?
One function, the decide function. It is indeed immutable. It does not change. But the inputs to that function are dynamic, yet cryptographically secured.
Okay, so how do you update the rules if the function is frozen?
The policy itself is a structured document that can be updated, but that update requires a cryptographic signature from a human authority holding the proper administrative key.
Ah, okay, so the rules can change, but the intern can't change them.
Exactly. The intern has zero access to the policy layer. If a crisis occurs, a human administrator signs a new policy granting the incident response agent temporary elevated capabilities to isolate that subnet.
Got it. And then what?
That signed policy propagates to the manager. The manager verifies the human administrator's signature using public key cryptography. Once it's verified, the new rules apply instantly.
Okay, that makes sense.
The rigidity of the decide function isn't about freezing the business. It's about guaranteeing that no action occurs unless the math proves it was authorized by a valid human or a predefined rule.
So the intern proposes, but the protocol decides.
Beautifully put, yes.
Yeah. I mean, this sounds bulletproof on paper, but I really want to dig into the actual code execution here. Because doing this without phoning home to AWS or Google Cloud to verify API keys sounds kind of impossible.
You'd think so, but this is where the developer's engineering restraint really shines.
How does this system manage identity, policy, and execution completely locally?
It's wild. The system requires zero external API dependencies to govern the fleet. Zero.
None. Seriously?
None. The cognitive part, our intern, can use a local model like Gemma 4 for development, meaning your proprietary data never even touches the internet.
Okay, but what about the governance part? The manager?
Built entirely using the Python standard library and battle-tested cryptography libraries like Pinnacle and Argon 2 Scythe.
Yeah, I noticed that in the repository. There are no massive database dependencies, no mandatory cloud services. It's just tight local code.
Extremely tight.
But let's play the role of the attacker for a second. If I am a hacker and I realize I cannot trick the manager with a clever prompt injection because the manager totally ignores the intern's reasoning, my next logical move is to steal someone's identity.
Right. Go around the logic.
Exactly. I'm not going to attack the wall. I'm going to steal a key. I'm going to forge a badge that says I am the CEO or that I'm an admin agent. How does this system defend against an identity heist?
That specific attack vector is actually formalized in their threat model. They call it Adversary A2, Forged Identity.
Okay, so they saw this coming.
Oh, absolutely. And the defense relies on those lightweight cryptography libraries you mentioned earlier. The entire root of trust in the system is an Argon 2-id strengthened master secret.
Okay, getting technical.
Right, and that secret derives a root ED25519 signing key.
Okay, let's translate that alphabet soup for the listeners who aren't currently writing cryptographic protocols on a Tuesday afternoon. What is the actual mechanism there? How does ED 25519 stop me from forging a badge?
Think of ED 25519 like a mathematically perfect wax seal on a royal decree.
A wax seal. I like that.
Right. So the root key is the king's actual signet ring. That ring is kept in a vault. It never touches the day-to-day operations.
Okay, the ring stays safe.
When an agent is spun up and given its identity and its permissions, let's say it's an agent allowed to trade 100 shares of Tesla. It doesn't get the ring.
Obviously not.
It gets a digital piece of paper with the king's wax seal on it. That seal cryptographically binds the agent's unique ID to the specific capability of trading those exact 100 shares.
Okay, so the agent only possesses a permission slip, not the authority to write new permission slips.
Precisely. Now, if an attacker compromises that agent and tries to alter the permission slip...
Like if they try to scratch out 100 shares and write 10,000 shares?
Yes. If they do that, the mathematical properties of the wax seal shatter. The signature breaks instantly.
Oh, wow.
So when that compromised agent slides its new forged proposal across the desk to the decide function, the function checks the broken seal against the public key of the king.
And the math just doesn't align.
The math fails. The decide function instantly returns B-locked.
Just dead in its tracks.
The compromised identity is stopped completely. A forged capability string cannot be executed because it lacks the valid cryptographic signature from the root authority.
That drastically shrinks the attack surface. It means security isn't about trying to outsmart a language model's emergent behavior, which, let's be honest, is a losing game.
It's a totally losing game. You'll never outprompt engineer an attacker.
Right. Instead, it's about relying on foundational mathematics that have literally secured the internet for decades.
Exactly.
Let's zoom out and look at the whole picture here, because the white paper breaks this down into this incredibly useful framework. I think they call it the 3 trust domains.
Yes, the 3 trust domains. And honestly, this is perhaps the most vital conceptual contribution of this project for anyone building enterprise AI right now.
It's a great mental model.
If you blur these lines, your system is vulnerable. So they are. The epistemic domain, the authority domain, and the execution domain.
Okay, walk us through the boundaries of each of those, and let's use a tangible scenario to ground it. Imagine a localized energy grid facing a sudden massive spike in load.
Oh, I like that.
Like possibly from a coordinated cyber attack trying to overload the physical transformers. Let's run that through the domains.
A perfect high-stakes scenario. Okay, so we start in the epistemic domain. Epistemic relates to knowledge, belief, and the degree of validation.
It's what the system thinks is happening.
Right. So the grid sensors feed data into the system. The knowledge compiler formats it. The language model, our intern, analyzes the data, recognizes the anomalous load spike, and deduces that a transformer is about to melt down.
Okay, so the intern formulates a belief, like we must immediately curtail power to the industrial sector to save the grid.
Yes. So the epistemic domain answers the question, is this belief correct? Or at least, how confident are we in this belief?
So it's all about probability and confidence scores at this stage.
Exactly. And the intern might be 99.9% confident, but that confidence means absolutely nothing when it crosses the boundary into the second area, the authority domain.
Because that domain doesn't care about confidence.
Not at all. The authority domain handles identity, capability, and policy. It answers a fundamentally different question. It asks, is this specific agent permitted to perform this specific action?
So we are back at the manager's desk.
We are at the manager's desk. The proposal to cut power crosses the desk. The decide function checks the agent's cryptographically signed wax seal.
And what does it see?
It sees the agent has the identity of grid monitor, but then it checks the corporate policy. And the policy dictates that a grid monitor can issue alerts, but only a human operator or an emergency executive agent can physically curtail power to the industrial sector.
Right, because cutting power to factories has massive financial and safety implications. You don't just let a monitor bot pull the plug.
Exactly. So the decide function looks at the grid monitor agent, sees it lacks the capability, and rejects the proposal.
It just drops it.
Drops it instantly. But let's say the system was designed correctly, and the grid monitor did what it was supposed to do and escalated the alert to the emergency executive agent.
Okay, so a new agent steps in.
Right. That executive agent submits the proposal. The decide function checks the new seal, identity matches, capability matches. The policy states that if grid load exceeds 95% of critical capacity, the executive agent is authorized to curtail power.
And all the cryptographic math checks out.
Yes. So the authority domain grants authorization.
Which brings us to the final boundary, the execution domain. The manager has stamped the paperwork. It's time to actually pull the plug.
The execution domain is what actually happens in reality. It contains the executor, the state mutations, the verifier, and the cryptographic evidence.
Okay, wait. I want to pause on this because in almost every piece of software I have ever seen, if the core logic authorizes an action and the API call fires, the system just assumes it worked.
Right. Fire and forget.
Yeah. You tell the function to save a file, the function returns true, and you just move on. Why does Sovereign Agent Fleet require an entirely separate domain just to verify execution?
Because of adversary A4, they call it executor deception.
Executor deception.
Yeah, what if the environment itself is compromised? What if the attacker didn't hack the intern and they didn't forge the manager's keys, but instead they compromised the actual physical switchboard?
Oh, wow. Yeah.
So the system tells the switchboard to cut the power. The compromised switchboard leaves the power on but sends a message back to the system saying, status 200, okay, power curtailed.
Ah, so the system believes it saved the grid, but the transformer is actually still overloading.
Precisely. So invariant 3 in their architecture is verification independence. The framework flat out refuses to believe the executor. It introduces an independent verifier.
How does that work?
You can think of this verifier as a deeply cynical bailiff.
A cynical bailiff. I love the personas in this system.
It helps it make sense, right? So the manager hands the bailiff the authorized paperwork. The executor claims the job is done. The bailiff physically walks over to the ledger, recomputes the expected state of the grid based on the cryptographically signed inputs, and checks the raw secondary sensor data to verify the power actually dropped.
So it's double-checking reality.
Yeah.
And if the bailiff sees the power still flowing, despite the executor claiming it was cut, it raises a critical alert.
It flags the executor deception immediately. The genius of Sovereign Agent Fleet is that an answer in one domain is never, ever mistaken for an answer in another.
Wow.
The intern's brilliant reasoning carries zero authority, and the manager's stamped authorization carries no assumption that the execution was actually performed truthfully. The boundaries are absolute.
That is true zero-trust architecture. Like, it's not just a marketing buzzword here. It is mathematically enforced at every single stage of the pipeline.
Absolutely.
Actually, let's trace that pipeline. Because visualizing how data moves through the system clarifies exactly why it is so robust. They outline this really detailed 9-stage pipeline from raw knowledge all the way to cryptographic evidence.
Yeah, let's follow a single piece of data through the entire gauntlet. Stage 1 is knowledge. This is the raw material.
Like what kind of material?
It could be markdown files detailing corporate policy, database records of stock prices, or raw sensor telemetry from our energy grid.
Okay, so that's stage 1. Stage 2 is compilation. What happens here?
Raw data is messy, right?
Yeah.
So compilation transforms that raw material into a structured, usable format, like a knowledge graph or a dense vector index.
Makes sense.
But here is the critical security mechanism. It's invariant 5, knowledge provenance. As the data is compiled, it sits behind a fail-closed verification gate.
What does fail closed mean in this context?
It means every single resulting node in the knowledge graph must be mathematically traceable back to its original source file.
Wait, really? So if a file is corrupted, or if an attacker tries to inject malicious code during the compilation phase,
the entire build process fails. It shuts down immediately. It will not allow the agent to reason over poisoned or unverified data.
that is incredibly strict. Okay, so once it's compiled safely, we move to stage 3, retrieval.
Right. The agent queries the knowledge graph to pull the specific facts it needs for its current task.
And stage 4 is cognition. This is where our intern wakes up.
The language model activates. It takes the retrieved facts, observes the current state of the environment, and performs its probabilistic reasoning. It thinks, it weighs options, it hallucinates, it deduces.
Right, it does its AI magic.
Yeah.
And that leads to stage 5, proposal.
Yep. The intern writes up the request. I propose we isolate server subnet delta.
Okay, so up to this point, through stages 1 through 5, we have been entirely inside the epistemic domain. We are dealing strictly with beliefs, probabilities, and ideas.
Exactly. And now we hit the hard wall. Stage 6, authorization. The proposal crosses into the authority domain.
The manager's desk?
The decide function takes over. It checks the identity, the cryptographic grant, our wax seal, and the deterministic policy.
As we discussed earlier, it completely ignores the intern's essay on why isolating the subnet is a brilliant idea.
Totally ignores it.
But wait, what if the policy isn't a simple yes or no? Like, what if the policy requires human oversight for critical action?
Then the decide function pauses the pipeline. If the policy dictates, human approval required for isolating subnets, the system stops. It demands a cryptographically signed approval record from a designated human operator.
Now, wait a second. A lot of enterprise software has a human-in-the-loop feature, but usually it's just a web dashboard where an admin clicks a big green approve button. How is this any different?
Oh, green approve button on a web dashboard is incredibly vulnerable. They call this adversary A3, approval forgery.
How does that work?
Well, an attacker could capture the network request generated by that button click and replay it later, or worse, pull the old bait and switch.
The bait and switch.
Yeah. They send a request to approve a $10 transaction. You click the green button. They intercept your approval, detach it from the $10 transaction, and secretly bind it to a $10,000 transaction.
Because the button click was just a generic token of approval, wasn't tied to the specifics.
Exactly. It's just a generic yes. In Sovereign Agent Fleet, the human approval record is a complex cryptographic object.
So it's much more than a click.
Right. When the human administrator signs the approval, their private key creates a signature that intrinsically binds the approval to the specific action ID, the exact capability being used, the timestamp, and the cryptographic hash of the artifact involved.
Wow. So if the attacker tries to take that signature and apply it to a different action,
the hash doesn't match the signature. It's mathematically impossible. The decide function detects the mismatch and instantly blocks the execution.
that is an incredibly elegant defense. The approval is completely non-transferable and tamper-evident. Okay, so stage 6 authorizes the action. Stage 7 is execution. The system actually fires the API call to the firewall to isolate the subnet.
And stage 8 is verification. Our cynical bailiff steps in, totally ignores the firewall's success message, and independently pings the subnet to prove it is actually offline.
I love the bailiff. And finally, stage 9, evidence. How does the system record all of this so that it can be audited later?
This is crucial.
Right, because if I'm an attacker who just failed to bypass the system, my final desperate move is to cover my tracks. I want to delete the logs showing I tried to forge a signature in the first place.
Naturally. And that brings us to invariant 4, evidence integrity. The system does not just write a simple line of text to a log file. It creates an XChat20 poly 3305 encrypted envelope.
Okay, unpack that alphabet soup for me. What is an XChat20 3305 envelope?
It is an incredibly fast, highly secure, authenticated encryption cipher.
Authenticated encryption, meaning what?
It ensures that not only is the data encrypted, so prying eyes can't read it, but it is also authenticated, meaning any tampering with the ciphertext will be instantly detected the moment you try to decrypt it.
Okay, so it's a sealed vault. What goes inside the envelope?
Inside the secure envelope, the system places the entire chain of events. The original proposal, the authorization grant, the human signature, the execution receipt, and the bailiff's verification result.
It literally gathers all the paperwork into one secure package.
Yes, but then it goes a step further. It takes that sealed envelope, cryptographically signs it, and links it to the previous entry in the system's ledger using a cryptographic hash.
A hash chain. Okay, let's explain how a hash chain works for the uninitiated, because it really is the bedrock of tamper-evident systems.
Sure. Imagine a physical chain made of glass links.
Glass links, okay.
Inside the glass of the second link is an exact microscopic photograph of the first link. Inside the third link is a photograph of the second link.
So they are visually logged together.
Right. So if you want to change something that happened in the first link, you have to shatter it to get inside.
But the moment you shatter the first link, the photograph inside the second link no longer matches reality. The discrepancy is instantly visible to anyone looking.
Exactly. In a cryptographic hash chain, every new log entry contains the mathematical hash of the previous log entry.
So if an attacker goes back in time and alters a log file from 3 days ago to hide their tracks,
the hash of that altered file completely changes, which means it no longer matches the hash recorded in the subsequent block. The entire mathematical chain fractures from that point forward.
and the tampering becomes glaringly obvious to any auditor verifying the chain.
The system perfectly preserves the reality of what occurred. That ledger becomes the undisputed reality for the next cycle.
Honestly, when you compare this beautifully designed state machine to the fragile duct tape scripts that a lot of companies are currently deploying as enterprise AI, the contrast is staggering.
It's night and day. We are moving past the novelty demo phase of artificial intelligence. We are entering the real deployment phase. And enterprise deployment requires uncompromising governance.
The rigor of this project is what truly elevates it from a neat hackathon idea to a production-ready blueprint. Like, they didn't just write a theoretical white paper. They subjected this architecture to punishing tests.
Oh, the testing methodology is fantastic.
Let's talk about the parametric sweep. They generated 6,000 enumerated points. What does that actually mean in practice?
A parametric sweep is a method of exhaustive testing. Because the core decide function is pure and deterministic, meaning it has no randomness, and relies on absolutely no unpredictable model input, they could map out the entire universe of possible conditions.
So they literally created a matrix of every possible scenario.
Yes, they ask, what if the cryptographic grant is present, but the signature is slightly corrupted? What if the identity matches perfectly, but the requested capability is out of scope for that specific role?
Right. What if everything is perfect, but the timestamp epoch has expired?
Exactly. They combined all these discrete dimensions and generated 6,000 distinct test cases.
And they ran all 6,000 through the decide function.
And for every single one of those 6,000 points, there were 0 false accepts.
0.
0. The system behaved exactly as the deterministic policy dictated. If it was supposed to block, it blocked. If it was supposed to authorize, it authorized.
That is phenomenal conformance testing. But honestly, conformance testing just proves the system does what you built it to do under predictable circumstances, right?
Right. It's the happy path, even if it's exhaustive.
Real-world attackers don't follow the rules.
Yeah.
They don't stay on the happy path. That's why I was so fascinated by Section 11.6 in their documentation, the blind adversary harness.
Oh, this is where the engineering crosses from meticulous to aggressive.
A blind adversary harness is a fuzzer, right?
Yes, and a fuzzer is essentially an agent of pure chaos. It doesn't know the rules of your system. It doesn't care about your invariants. Its only goal is to throw massive amounts of garbage, malformed data, and unexpected inputs at your program to see if it can break the logic.
Just looking for a crash that allows an exploit.
Exactly. So instead of testing specific scenarios like expired timestamp, the fuzzer is just throwing random strings of alphanumeric noise at the vault door to see if the lock glitches open.
So how did they set this up?
They built a fuzzer that randomly generated 5,000 completely malformed, forged, and chaotic requests.
5,000.
5,000. We are talking untrusted cryptographic keys, garbage capability strings that don't map to any known function, epochs from the year 1970, epochs from the year 3000.
Just absolute noise.
Total noise. It took all 5,000 of these chaotic attack vectors and hurled them at the decide function. The goal was simple. Can this chaos trick the system into authorizing an action without a valid grant?
And the result of the blind fuzzing?
0 false authorizations.
Wow.
Across 5,000 randomized, unstructured attacks, the decide function never flinched. The mathematical walls held firm.
That is deeply satisfying to hear. It proves that this isn't just a collection of patch fixes or, if-then statements trying to anticipate every single hack. It is a fundamental structural defense.
Exactly. It's foundational.
And that structural defense is what unlocks the next massive advantage of this architecture. It's cross-domain generality. I think they refer to this in the paper as the M0 meta-invariant.
Yes. And this is so important because a lot of agent frameworks are highly coupled to their specific use case.
What do you mean by that?
Well, if you build a framework specifically to govern coding agents, that framework is entirely useless if you want to deploy agents for financial trading.
Right.
The logic is just too entangled with the domain.
Right. The coding rules don't apply to the stock market.
Exactly. But Sovereign Agent Fleet took this exact same governance substrate, the exact same frozen decide function we just watched survive 5,000 fuzzer attacks, and they ran it across 6 completely independent enterprise workloads.
6 different workloads. Let's walk through those. Finance was their flagship exemplar, right?
Hey, it was. They built a sovereign prediction market venue. It had a matching engine, quantitative reasoning, and risk layers. The agents were trying to execute high-frequency financial trades.
And the decide function handled it.
Successfully governed those agents, ensuring they didn't violate trading limits or bypass risk checks.
See, that alone would be an impressive hackathon submission. Just a secure finance bot. But then they ripped the finance domain out entirely and swapped in an incident response workload.
Cybersecurity and server remediation. The agents were now analyzing network logs and proposing firewall changes. And without editing the central decide function at all, it flawlessly governed the incident response agents.
So it protected the assets, required the human approvals for critical server isolations, and logged the cryptographic evidence. All the exact same way.
Yes. Then they swapped it again, supply chain operations. Then scientific hypothesis reasoning. Then agent introspection. And finally, the energy grid demand response scenario we walked through earlier.
So that's 6 completely different shapes of data, 6 completely different operational stakes, all governed by the exact same mathematical rule. Model output does not equal authorization.
It is a stunning proof of concept. It demonstrates that the authority boundary is a fundamental computer science primitive.
By separating the domains so cleanly, you can build adapters for literally any industry. The substrate doesn't care if it's protecting a megawatt transformer or a stock portfolio. It only cares about the math.
And this modularity gives developers total data sovereignty. You aren't locked into a single AI provider or a single cloud ecosystem.
Which is huge for vendor locking concerns.
Huge. Because the control plane is strictly local, you can plug and play the cognitive brains as the technology evolves. If Anthropic releases a significantly better model tomorrow, you just fire the old intern and hire the new one.
But the manager stays exactly the same. Your security posture doesn't change one bit.
You own the sovereignty of your system. You can even use massive cloud-based language models for the heavy cognitive lifting, passing non-sensitive data up to the cloud for processing, but the execution and the cryptographic authority remain completely locked down on your local hardware.
The presentation of this project is just as impressive as the code itself. As a hackathon submission, it reads like a peer-reviewed paper from a major research institution.
The documentation is top tier.
They documented their decision-making process meticulously, logging decisions D1 through D30. They clearly state their invariants, their threat models, and their claims. But what I found most refreshing is that they explicitly state what their architecture does not guarantee.
The claims and guarantees statement. It is the hallmark of mature, disciplined engineering to openly acknowledge the boundaries of a system.
Right. They state clearly that their framework does not guarantee that the language model's reasoning is correct.
It does not guarantee that the source knowledge fed into the system is true.
And crucially, it does not guarantee that the corporate policy itself is correctly specified.
Right. If a human administrator writes a terrible, legally disastrous policy that states, always sell all our stock on Tuesdays, and cryptographically signs it.
The protocol will flawlessly enforce that terrible policy.
Exactly. The protocol guarantees that the policy is faithfully enforced. It does not possess the capability to judge whether that policy is wise.
Which brings us to a fascinating, almost philosophical paradox they explore in the paper, which they term the unintuitive result.
The unintuitive result. This is such a deep concept.
It's the idea that a perfectly governed, mathematically secure system can still execute exactly the wrong action. Walk us through this, because I feel like it challenges a lot of assumptions we have about AI safety.
Let's return to our brilliant intern. Imagine the intern does their research, but the underlying textbook they are reading has been subtly altered. It contains false information.
So the epistemic knowledge is fundamentally wrong from the start.
Right. The intern, being perfectly logical, reasons flawlessly based on that false information and drafts a proposal. The proposal crosses the desk to the manager.
And the manager checks the policy, verifies the agent's cryptographic identity, confirms the capability matches the request. Everything aligns perfectly.
The math is sound. The action is authorized.
So the authority integrity is perfectly maintained.
The manager hands the paperwork to the executor. The executor performs the action exactly as requested. The cynical bailiff verifies that the action was performed correctly and signs the ledger.
The execution integrity is perfectly maintained.
And yet, the final outcome is disastrous. The company loses millions, or the server is permanently bricked because the original premise the intern relied on was flawed.
Wow.
The system maintained perfect authority and perfect execution integrity while still producing a deeply incorrect outcome.
The system was perfectly governed, utterly secure against hackers, cryptographically audited so you know exactly who did it, and it still drove the car right off the cliff.
This is why separating the 3 trust domains is so vital. It forces developers to realize that security, provenance, and truth are not interchangeable concepts.
You can have impenetrable security and perfect provenance, tracing exactly where the data came from, and still completely lack truth.
Exactly.
We spend so much time in the enterprise space worrying about AI agents breaking out of their sandboxes or hackers forging API keys. But sometimes the most devastating danger isn't a hack. It's simply that the AI is confidently wrong, and we have built a perfectly secure automated pipeline to instantly execute its wrong ideas at scale.
Which segues directly into the final unsolved problem they present in their research. Adversary A6. Knowledge poisoning.
Knowledge poisoning.
This is the absolute frontier of AI security.
If I'm an advanced persistent threat actor and I read this white paper, I realize very quickly that I am never going to break the 825519 cryptography.
No, the math is too strong.
I am never going to trick the decide function. The wall is simply too high. So how do I compromise the enterprise? I poison the well.
If the architecture perfectly secures the authorization and the execution, the attacker's path of least resistance is to silently manipulate the data the AI learns from.
If I can subtly alter the markdown files in the corporate wiki, or manipulate the database records, or inject false facts into the network logs that the model uses to build its knowledge graph.
You don't need to break the cryptography.
I don't need to steal a key. I just trick the intern into believing a catastrophic idea is actually a brilliant optimization.
Precisely. If a perfectly governed AI strictly follows the rules but reasons from a secretly manipulated document, it will flawlessly execute your terrible idea.
And the system's own cryptographic audit trail will simply prove that the wrong thing was legitimately authorized and correctly executed by the rules.
It will perfectly mathematically document its own disaster.
That is chilling. How do we even defend against that?
Well, the authors propose several future defenses. They suggest requiring multi-author cryptographic attestation at the moment a document is ingested, ensuring no single compromised employee can alter a file.
Okay, that helps with internal threats.
They also suggest building systems that perform cross-document contradiction detection over the compiled graph, flagging logical inconsistencies before the model can even reason on them.
Like fact-checking itself.
Right. And they propose establishing strict knowledge uncertainty bounds, where any proposal based on conflicting data is automatically escalated to a human, regardless of policy.
But they admit, right in the paper, that this remains an open, unsolved problem.
It is the holy grail of epistemic integrity. How do you mathematically prove that a semantic sentence is objectively true?
You can't. Not with math alone.
You can prove who wrote the sentence. You can prove exactly when it was written. You can prove with absolute mathematical certainty that it hasn't been tampered with since it was written. But proving that the contents of the sentence are true, that bridges computer science into the realm of philosophy.
And acknowledging that profound limitation, rather than slapping a marketing buzzword on it and claiming 100% secure AI, is exactly what makes this hackathon submission so compelling.
It's just honest engineering.
It bounds its claims to exactly what the architecture achieves: verifiable, mathematically secure local authority over execution.
It provides the foundational blueprint that enterprises desperately need to move autonomous agents out of the laboratory and into production safely. It wrestles the wild, probabilistic nature of modern AI into a deterministic, auditable framework.
If you are a developer, an enterprise architect, or a CTO losing sleep over data sovereignty, I strongly urge you to examine this repository. Search for ClearDaniel/Sovereign Agent Fleet.
Read the Sovereign Knowledge Systems white paper. Look at the elegance of the decide function.
And if you're participating in or following the All Things Agentic Hackathon, this highly fortified project demands your close attention. It's a masterclass in secure design.
It truly is a glimpse into the necessary future of agentic infrastructure. You get to harness the brilliant intern, but the strict, unyielding manager is firmly in charge.
We started this exploration talking about the X-ray machine. The desire for clear, visible, binary answers in a world of complex probabilities. Sovereign Agent Fleet gives enterprises that exact X-ray vision for the execution of AI actions.
The execution is transparent.
We can look at the ledger and see exactly who authorized what, cryptographically proven beyond a shadow of a doubt, but the AI's mind itself, the epistemic domain, that remains a murky, probabilistic black box.
It always will be.
So, as you design the future of your organization's infrastructure, the question that lingers is this: in a world where we can now build a perfect, mathematically impenetrable fortress to guard our actions, how do we build a fortress to guard our truth?
A phenomenal question to leave us on.
Keep analyzing, keep building securely, and we will catch you next time on The Deep Dive.